Sending. It says it's sending. Is it sending to the correct place?
No.
All right. Now we're going to the correct place?
Mm-hmm.
All right. All right. Okay. Hopefully.
Okay.
All right.
All right. We'll give people a second.
So while everyone's switching, I have, for those of you who are already here, I have a question. I have been gifted from my husband a 1 day park hopper ticket for Disney World to speed run the parks. I only have 1 day. And I've been watching a bunch of YouTubes and reels of people who have a variety of challenges they have to accomplish. And I'm trying to figure out, given just 1 day and the ability to go to all four parks,
in
what.
Disney World.
Mm-hmm. So what.
Have you ever been to Disney World?
Oh yeah, many times.
Okay. All right. Well, then you know more than everybody. I mean, for me, Epcot Center is the best. I
Would
don't
you?
really care for the rides.
Okay, you're not a rides person.
I I it's a fine, ride a bit, sure. After a while you get a little nauseated. Um,
See,
yeah.
I have a really crappy inner ear from being one of those children who had constant ear infections. Go figure, me sick as a child.
Mhm.
Um, and so like I really don't get motion sick.
Hmm. Yeah, I don't get motion sick either. Like I can read in a car forever. It's no
Yeah,
problem.
same.
I could read on a boat in choppy weather. No problem. But there's something about amusement park rides after several hours that it does start to build in me.
Okay.
Um, so I don't know, it's like being drunk. Like after a while, like in the beginning, you're like, woohoo, I enjoy this feeling. After a while, you're like, yeah, I'm too old for this. Um, so anyway, so for me, I wouldn't just hit rides hard. But if that's what you want to do, yeah, I have no recommendations for you. And a lot of it's new. I mean, I think I'm closing in on 15 years since I took my kids to Disney World. So,
Yeah. Anyways, if
um,
any of you have ideas. So there isn't new Star Wars content since I was last there, but I've only gotten to ride Rise of the Resistance when the Kylo Ren animatronic was broken. So I'm
mm,
definitely going to try and do that in hopes that I'll actually get to see Kylo Ren in his animatronic glory. Um, yeah, I'm considering doing a reprieve of what Annie, Susie, and I did a number of years ago when we went to Florida to watch a bunch of rockets launch, and zero rockets launched. And so we went to Disney World and ran around going, "Is this a rocket?" So I'm considering, but I don't know. It's an idea.
all right, I think we can get started now.
All right, all right. I This is 7:18,
19,
19.
719.
Good Lord, brains, brains. All right, new audio file app 719. I'm pressing record on my audio. I am pressing record on the video. We are recording.
I am doing the same. Astronomy Cast, episode 719, the Galaxy series, Spiral Galaxies. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain. I'm the publisher of Universe Today. With me, as always, is Dr. Pamela, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am doing well. When folks are hearing this episode, you're going to be off in Japan,
Yes.
and that is amazing.
Yeah, we're making up for that trip. So, 4 years ago, in 2020, I booked a trip. Actually, in 2019, I booked a trip to Japan for my son, with my son,
Yeah.
and then COVID hit and things got pretty dicey, and so we decided to cancel the trip. And it's been 4 years, and now, like, what's COVID? Who remembers that anymore? So so we're going to do it again. And now he's older and a lot wiser, and I think it's going to be a really fun time. So
Yeah.
yeah, by the time you listen to this, we will have been in Japan for a week. Um, and people are like, "Are you going to do this? Are you going to do that?" I'm like, "I have no plans. This is purely vacation. I'm if I run across JAXA as I turn a corner in some neighborhood, then sure, I'll walk in. But I'm not booking things, doing interviews, any of that. I'm going to bring a camera, but apart from that, no, this is just purely fun. I want to eat some tasty sushi and noodles.
Oh,
I want to walk around cool parks and temples. I want to ride bullet trains, and I want to meet people there. So, yeah,
I I have to say I haven't found sushi there that was any better than what I've gotten in the US, other than you can get fugu there, which you can't get in the US.
no thanks.
But the ramen, I had
Yeah,
ramen that is the stuff of dreams, and may you
yes,
find such hole in
I'm
the
looking
wall
forward to
ramen
that.
places.
Yeah, yeah, that sounds great. Our Galaxy series continues on to spirals. In fact, you're living in one right now, but telescopes show us the various shapes and sizes these galaxies come in. Thanks to JWST, we are learning how these spirals got big early on in the universe. And we'll talk about it in a second, but it's time for a break.
I'm drinking, hold on. Thank you.
And we're back. All right, Pamela, spiral galaxies. And this is obviously familiar territory because we live in one.
We do, although living in it has made it particularly challenging to study.
Right.
Like, we figured out there's a bar in the center of our galaxy only within the past couple of decades. We still see every few years they change their mind on exactly how far we are from the core of the
Right.
galaxy.
How many arms the Milky Way has
Right,
is
right.
the last episode we talked about, different controversies that are still unfolding.
Yeah,
And one of those is how many spiral arms does the Milky Way have? This is a question
yeah.
that is it two? Is it four? Is it two, but then two other kind of arms that are broken off of it? It is a tricky question because you're embedded inside. Like, quick,
Yes.
imagine yourself in a random house. What color is the paint on the outside of your house?
It's a
You know,
challenge. It's a
it is
challenge.
challenge. Yeah, yeah. Maybe you'll see it in reflected windows of cars as they drive by.
And what makes the challenge all the more fun is we have this Andromeda galaxy looming so very close. And at first glance, it seems to be so much bigger than we are. And yet, every time we revise our mass estimates, it seems that
Right.
our galaxy and Andromeda get closer and closer in size. And so it just turns out trying to understand things that take more than one field of view of a telescope to look at is really hard. Really hard.
Yeah, I love those images of what Andromeda would look like if it was bright, like the full
Yeah.
moon, and you could see it. It is the size of, what is it, like nine full moons in the sky? It's gigantic.
Yeah. Yeah. And and then there's also the challenge of the size of galaxies varies depending on what color of light you're looking in. And
Mm,
this has been one of the challenges with classifying galaxies, especially spiral galaxies. So the old school, still taught, tried and true way of classifying spiral galaxies is the Hubble tuning fork diagram. And in this diagram, you have ellipticals of varying roundness to flatness that eventually become what's called a lenticular galaxy, where you have a nucleus in the center and then just like a disk of no structure around it. And then it forks, thus the tuning fork part of the analogy. And the arms on the galaxies for the spirals and the barred spirals just get more and more unwound. But it turns out if you look at galaxies in different colors of light, you're able to see their arms in different degrees. And so when it comes to trying to figure out how do we write software to classify galaxies, how do we get human beings to classify galaxies, it is a glorious disaster.
Right, right. And I mean, it's a mess because galaxies are weird.
Yeah. And
Yeah, it's not humans. It's a galaxy's problem.
go galaxies.
Right. Yeah. Keep being weird,
Yeah,
galaxies.
yeah.
Um, so then how do they form? I mean, we look at these. I mean, there's some beautiful examples, the Whirlpool Galaxy, the Pinwheel Galaxy. They're nice face-on spiral galaxies where we look just right down onto them, as well as ones that are farther away that are less famous, that are equally as beautiful and distinct. How do we get this weird shape in some of the structures that we see?
So, how exactly you go from either blob of mass to spiral galaxy or a whole bunch of dwarf galaxies merging together, which is how these probably form, but the universe likes to have exceptions to every rule, and I'm just going to throw that out there. There are always exceptions.
Yeah.
Um it looks like we get spiral galaxies through the merger with the correct angular momentum coming together to set things in a nice coherent spiral. Then it gets trickstery though, because spirals come in different varieties, separate from just how much of their arms splayed out. We have what are called flocculent spiral galaxies, which are spiral galaxies. When you look at them, you see there is what appears to be feathers, flocculent, of spirally bits all throughout them, but there isn't a clearly defined pair or multitude of arms. It's just like arm bits all the way down. Then you have galaxies usually that have a companion. We think that it's the gravitational interactions that drive the spiral density waves that create these grand design spirals, which have two arms, only two arms, perfectly formed, maybe
And the
bits of
number shall
stuff.
be two.
And the number shall
Two.
be two, and only
Two
two.
was the arms. Yes.
And and
Yeah.
and so going between these extremes is every possible version of messy and glorious. And then we see some spiral galaxies have rings in their centers, have bars in their centers. And again, this is all driven, we think, from the gravity of companions. And then we have things like the Seyfert 1 and 2 galaxies that have active galactic nuclei that are shooting out jets of radio waves. Um, Spirals are just out there trying to show off. They are the drama queens, they are the pageant
Right.
queens.
Right. They're the peacocks of the
Yeah.
galaxy world. Yeah. Um, Now we're gonna talk about this some more, but it's time for another break. And we're back. So this shape, I mean, it really looks like someone is winding up a bunch of stars from the middle, and you get these spiral arms that form. What are the spiral arms?
They are actually just places where material lingers as it goes on its orbit around and around a galaxy. It's not that galaxies have solid disk rotation where those arms are intact and the whole thing is bulk rotating like a pinwheel. That is not happening. I just want to make that
Right.
very clear.
Yeah.
The
Yeah.
structure might look like a pinwheel, it is not rotating like a pinwheel. So, what's happening is as material goes around and around the core, there are regions that have higher density. The regions that have higher density accelerate material towards them. So it gets there faster and then holds on to it so it slows down as it exits. So the amount of time that material stays in the arms is increased compared to the amount of time that it spends on the other parts of its orbit. So you can have material zoom into, I don't know why I said that like that. You can have material that zooms into a galaxy's arm, passes through ever so slowly, interacting a lot, star formation gets triggered in arms, and then passes out the other side until it gets to the next arm, rinse and repeat.
Yeah. So like analogy that I love to use, like imagine you're in a balloon above the Super Bowl
Yeah.
and you're looking down and the wave is happening. I don't know if they do the wave at the Super Bowl, but imagine the wave is happening. So you've got human beings standing up, shaking their banners, cheering, and then sitting back down again. And you're seeing this wave propagate through the entire arena. And from your blimp view, it looks like something is turning inside the stadium, but it is not what's turning. It is the people standing up and sitting back down, creating this illusion. And that's the same thing as what's happening with the spiral galaxy. Now, the whole galaxy can be spinning. That's a separate thing. But those spiral arms that you're seeing are these density waves that are just rotating through as all of the stars are doing the wave.
And
they take their time. They have their turn in the arms, and then times when they're not in the arms.
And to be clear, the majority of material in a spiral galaxy, not all, there's always exceptions. That's just going to keep coming up. The majority of material in a spiral galaxy will be orbiting all in one direction, like cars on a racetrack, should in theory all be going in the same direction. And what we're seeing is all these things that are going more or less in the same direction are just lingering longer, where there's a higher amount of mass to pull them in and hold on to them as they try to continue their orbit.
But we clearly see these star forming regions in the spiral arms of these galaxies. So what's that about?
So if you think about it, star formation gets triggered through interactions, through shocks, through something taking a nice stable cloud of gas that is supported through the balance of gravity inwards and thermal pressure outwards. Doesn't take a lot to knock that kind of a cloud out of equilibrium. So as these nice friendly clouds enter the region of crowding, the probability that something that got there before them is going to have a supernova go off, the probability that a couple of these clouds are going to interact with each other and knock each other out of equilibrium is a whole lot higher than when that cloud is all by itself in the space between arms. So when these clouds get to the high density region of the arm, they tend to get knocked around, and that knocks them out of that very careful thermo gas dynamics versus gravity balancing act. And you get
right. So parts of the cloud are pulled in, and then you get the densities that can begin and trigger the star formation.
Or it could literally just be the shock wave from a supernova hitting one of these clouds, and there's a lot more supernova going off in the arms where you have a lot more star formation, and supernovae go off when you have star formation and those first giant stars die.
Right. It's this cycle that just gets rolling. It's crazy. Like, I just sort of imagine this wave sweeping past. And as the wave is sweeping past through space, you're getting clouds of stars start to form in this, and then supernova are going off, and this triggers more star formation, and then the wave passes and the fuel is depleted and you have less stars in that region, but now the next region gets filled with stars. It's a very, I don't know, very evocative concept to think about.
A better analogy might be a traffic jam. I don't know if you've ever been like driving along on a road trip, full tilt boogie, and all of a sudden 3 miles ahead, there is an accident on the complete other side of the highway. There's no reason for your side of the highway to slow down. But it turns out, because human beings are human beings, they will race forward and end up piling up. And then when they get close to that accident, they're like, must look.
Yeah. What is it? How many police cars? Yeah.
And so you end up with this compression wave triggered by looky-loos, and that causes a compression of cars in that one place. Well, here it's the gravitational wave of looking at the car accident that's causing the compression and the lingering. In the galaxy, it's the gravitational pull of all the cool stuff going on that has mass and is holding you in place.
All right, we're going to talk about this some more, but it's time for another break. And we're back. So once again, JWST has joined in the hunt for galaxies. And because these things are fairly large and fairly bright, it's seeing spiral
Yeah.
galaxies early on in the universe.
Yeah.
So give me some surprising discoveries about spiral galaxies thanks to JWST.
So we thought that they would come very slowly into being. It would take couple billion years for them to exist, built up through the slow aggregation of smaller systems into larger systems. And it turns out something
Nope.
happened. We don't know exactly what happened. JWST is still looking, and hundreds of millions of years, not a billion years, hundreds of millions of years, we're already starting to see spiral structure. It's not perfect, at least not what we can see through JWST, which admittedly isn't that many pixels across, but still, it's enough that we can see the spiral structure.
Wow.
And and so it turns out that somehow these things are forming faster and earlier than we thought through means that are still being defined. And there's so much to figure out. Like if you look at the velocity curve of a dwarf irregular galaxy, they have the same velocity curve structure as a spiral galaxy. So these dwarf irregulars that look like dead bugs on the sky have stars that are mostly going around and around in one direction in a known way related to dark matter. And then we see spiral galaxies. And so how are these things merging to get us bigger systems? Are they forming just big and spiral? We don't know. We're figuring all this out. It's a
Hmm.
really cool time to realize everything we knew was wrong and we get to start over and try again.
Right. Right. And the other thing that this is fairly recent news. I don't know if you have been following this story, but they've found that the galaxies have bars as
Yes.
well early on,
And that
which again,
implies
it was not
companions.
right, right, which was what you were talking about earlier, that
Yeah.
there's some kind of interaction between the galaxy and its companions leading to this bar forming in the middle. What is this bar?
There are so many different papers that don't say the same thing. So what it is, for reasons that have many explanations, and I am not going to make a personal opinion right now because someone will send me a nasty letter.
Right,
There are galaxies, including our own, that have a companion and have a structure in the center that is linear and radiating out from the black hole. And then these spiral structures appear to spiral off of the ends of this bar. That
right.
companion is the consistent part. Exactly how the barred structure forms, there's lots of theories. I'm just going to leave it there and not
Right,
deal
right.
with the letters in my inbox.
Yeah. So it's a couple of things. One is that, about two-thirds of galaxies have bars,
Mm-hmm.
and they appear to come and go over time.
Yes. Yes. It's a
So,
transient phase, which is
right.
consistent with the companion galaxies coming and going, changing in distance, getting consumed actively.
Yeah, yeah. And so you can get some event that causes the bar to buckle, to collapse in on itself and disappear again. And then other times the bar will start to spread out and stretch out, and the arms end up at the end of the bar. So it's a weird thing. Spirals have
Yeah.
them. Um, and and yet, as you know, I mentioned this, that now there's observations that they're seeing these spiral bars in galaxies that are under 1 billion years old. Like you should not have seen these mature structures in galaxies, and yet there they are. Um, so once again, the universe is speed running its large scale structures, its more mature structures, and this is a surprise.
And what I'm really loving is we already knew quasars, active galaxies, were much more common in the early universe. We haven't been able to really make out consistently the structure around them. Studies that use Sloan Digital Sky Survey to do extremely statistically rigorous looks found that there were the same fraction of mergers among quasars as non quasars. So there's just something special in the systems with quasars that causes them but there's something of the early universe. There was more gas then, there was more material then. And so we have all of these weird things that were high energy events creating amazing forces. There was more stuff around to do the mergers that hadn't formed large scale structures yet, um, large galaxies yet, not just large scale structure. It
Now oh, go ahead. Sorry.
it
Were you
was
done?
basically the pottery waiting to be formed.
Right. We talked a lot about dark matter in the last episode, and I think we
Hmm.
should definitely talk about dark matter as it relates to a spiral galaxy as well. So, what role does dark matter play in the behavior of the galaxy?
It changes how they rotate, or it changes, I guess, a better way to put it, how the stars at a variety of different distances orbit around the galaxy. This was one of the things discovered by Vera Rubin. And what's remarkable here is Vera Rubin was trying very hard to do non-confrontational research.
Right.
She moved away from other topics because she was like, nope, don't want to deal with the the politics. Just want to do
Yeah.
science.
Yeah.
And she quite accidentally discovered that as you move out from the core of a galaxy and you get more and more material inside your orbit, it was expected that things would be uh, going at lower and lower orbital velocities. And
Like the
it's
solar system.
like the solar system. And
Right.
instead, what happens is it just flattens off. Just flattens off. So the
Right.
outer parts of galaxies, out to the greatest distances we can see, beyond a certain point, everything just keeps rotating at the same rate.
Right.
And this is because the distribution of dark matter is such that it's counterbalancing what we see with the baryonic luminous matter and changing the rotation curves. And so we're essentially trying to map out the distribution of material we can't otherwise see by looking at the rates at which stars, globular clusters, clouds of neutral gas are going round and around our Milky Way. And poor Vera Rubin, who was trying to do non confrontational research, discovered this.
Right.
Ended up
Yeah.
having to spend about a decade proving that she was right. Along the way, she demonstrated that work done in the 30s by Fritz Zwicky on galaxy clusters was the exact same effect. And then the poor woman never got the Nobel Prize for everything that she went through. She got many awards, but it is generally seen as a great oversight that she didn't get the Nobel Prize for
Yeah.
what she did.
I want to sort of just reiterate this discovery because I think it is so foundational,
Yeah,
and you can't hear this and roll your eyes at dark matter,
right.
which is what I see a lot of in the comments. And so if you're like, astronomers just make up this thing called dark matter for blah blah blah. You know what? No, 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 absolutely not. That is incorrect. And let me sort of give you this insight, right? You measure, like here in the solar system, the Earth is going at 30 kilometers per second
Yeah,
around the sun. Neptune is going 5 kilometers per second around the sun. There is this drop off in the velocities of the planets as you get farther from the sun. It is this steady line going downward that measures the velocities. You look at a galaxy. Yeah, close to the center of the galaxy, the rotation rate is increasing, and then you hit this point where you then, as you measure outward, it's like, what is it, 250 kilometers per second, and a little farther away it's 250 kilometers per second, a little farther away,
still.
250, still the same, or is it 220? I forget the exact number. It's 220 or 250, whatever. And it remains the same
Yeah,
all the way out to the outskirts of the galaxy. And so the galaxy is not a little solar system. It is something else.
yeah,
And you can't get that rotation curve without 10 times the mass in the galaxy. That if there was, you could see 10 times the mass in black holes all around the galaxy and they were visible somehow, then that would explain it.
yeah.
But
It's the equivalent amount of matter of taking one Acme brick per solar system sized volume in the outer
right.
galaxy. So you can imagine just all these Acme bricks floating around. Um, and the Matcha project has gone looking for the universal version, which is neutron stars, stellar mass black holes, white dwarfs, and hasn't found them.
Yeah, and so you take a person who like doesn't who rolls their eyes at
Yeah.
this, and you say, okay, fine. So how does this work? How do you get the stars not slowing down in their orbital velocity like you would see in a solar system?
Right.
And then the person has to say, oh, I don't know. Right. Done. You now are part of the dark matter belief system, right? You like, weird observation. Why is this happening? I don't know. Good enough. Join the club. Here's your membership card. You're now one of us. And so, yeah, it's called dark matter, but who knows what it could be, as you said, particles. It could be black holes, and it could be that we don't understand gravity at the longest scales. Doesn't
And it
matter.
can be a
Still dark matter.
combination.
It
I
could
just
it
want
is
to make that
almost
clear.
certainly a
Yes.
combination of
Yeah.
all of them. And done. You are part of the confusion that nobody knows what this thing is. And yet people can make these observations with relatively small telescopes. Vera Rubin did it in the, almost 100 years ago. And yet
And
here
now
we are still arguing about what it is.
and little tiny radio telescopes that universities have allow us to go even further out in the galaxy than what Vera Rubin initially did with optical light, because we can start seeing the neutral gas that is the furthest stuff out in our galaxy. And so, yeah, grab yourself a small optical telescope and a small radio telescope, and you're done. You can prove there has to be something invisible out there affecting the rotation curve.
And there's one last piece of spiral galaxy that I think is really important, which is the monster at the heart of them.
And as recently as the 1990s, people were drawing on overhead sheets little tiny monsters, usually with antennae and giant mouths, like vomiting jets out of the cores of spiral galaxies.
Right.
So much has been lost now that professors aren't hand drawing on overhead sheets. Um, it's truly a lost art, and we are suffering so many fewer cartoons as a result of it.
Right.
So yeah, spiral galaxies, there is a relationship, and this works for ellipticals as well. There's a relationship between the size of the bulge and the size of the supermassive black hole in the center. There are some galaxies, like less than 10 last I looked, that look like quite maybe possibly it could be they don't actually have a supermassive black hole and they don't have a bulge, but still
Right.
working on it.
Yeah.
But
Millions do, 10 don't.
right, exactly.
Yeah.
And so when you see these systems with large bulges in the core with lots of high velocity stars in those bulges, they're going to have the big supermassive black holes. Smaller bulge, lower motion, smaller supermassive black hole. And yeah, and what's neat is depending on the angle that we're able to look in on a supermassive black hole that's feeding, we get all sorts of different cool effects. So if you have a system that's edge on and has a supermassive black hole in the center, it's called a Seyfert-2. They're kind of boring. They don't have very exciting lines that do very much, but they are active and they show up in the radio in new and interesting ways. Now tilt that towards us and you start to get what's called a Seyfert-1. Tilt it straight towards us and give it a really powerful jet, and you start to get what's called a blazar. And here, because of the distance that the time that it takes light from the far jet to get to us and the time that it takes for light from the near jet to get to us, it gives the perspective of faster than light motion between the two ends of the jet. So there's just really cool physics.
Yeah, that's really awesome. All right. Well, I think we've covered spiral galaxies. And so next week, we pick up the story with the giant elliptical galaxies. Thanks, Pamela.
Thank you, Fraser. And thank you to all the folks out there that support us through Patreon. We really rely on you so very much. Beth pulled together putting these 3 episodes for us on a dime when I told her yesterday.
Surprise.
Yeah, guess what? And Rich is out there doing all of the editing, hiding so many blunders. We thank you, Rich. Allie's out there helping with our YouTube channel. It takes a team to make this happen. This week, I want to thank Kimberly Reich, Disastrina, Jeff Wilson, Tim Garish, Greg Wild, John Drake, Robert Cordova, Paul D. Disney, Veronica Cure, Michelle Cullen, Philip Walker, Benjamin Davies, Dwight Ilk, Brian Kilby, Daniel Loosely, Sabra Lark, Sydney Walker, David Boggety, Evil Milky, Justin S., Maxime Levitt, Hal McKinney, Bebop Apocalypse. I love that one. Daniel Philippon, Bruno Letts, Ruben McCarthy, Larry Dortz, Bob Zaksky, Time Lord I. Rowe, Frank Stewart, and Jason Kadakis. Folks, you donated $10. We are grateful, and this means I mispronounce your names. I am sorry.
You won. Thanks, everyone, and we'll see you next week.
Bye-bye. And then they saved. All right, so we're going to have to do the stop the stream, start the stream dance again. We have learned tricks. We are going to stop long enough to make sure this stream stopped on YouTube.
Right.
So everyone on Twitch, don't go anywhere. I'm so sorry we're about to subject you to another ad. It's just going to be the way it is. I'm going to switch my settings and
we'll see you on the 720. Make sure if it doesn't say 720, it's not legitimate.
Yeah, exactly. So head over. Did it work?